phone to your cameras, and pretty much every technology, every electronics that you see around is based on silicon. But silicon has already come to a point where you cannot further advance the technology, right? Now I'll build on this a little further, but first understand that what is called, if somebody has to become superpower or tomorrow's superpower, what are the key elements needed, right? You need, as Devjani explained, you need access to technology, you need ownership on the technology. If you see the current manufacturing strategy, the current strategy in pretty much every sector, including semicon or electronics, we are doing manufacturing or embarking on manufacturing using licensed technology. Now, if we develop or we manufacture using licensed technology, there is an umbilical cord which is built in from the place, the country or the organization from where the technology has been licensed, and that umbilical cord can always be pulled back or twisted against a nation. So the question is, or the fundamental question is, can a democracy like India or a largest democracy like India become a superpower with such an umbilical cord built in? While the manufacturing approach is important to build an ecosystem, but at the same time we have to put efforts in addressing this umbilical cord going forward in the longer term. So the question is, how do we address this? The answer is, we have to jump the roadmap and work on things which are targeted in future. This is what Devjani explained as disruptive technologies. So we jump the roadmap, rather always playing the catch-up game. We jump the roadmap as well parallelly, and develop self-reliance in areas which are projected to take lead in future. So the path is very clear. You want to become technology leader, you invest in future tech, you own intellectual properties, then you manufacture using homegrown technology. In that case, there is no umbilical cord, there is no arm twisting, right? So the bottom line is, if you want to become a leader or tech leader, you have to invest in the next generation. Now, this is where the difference between, or the transition from silicon to 2D materials come in context of the semicon leadership. So, as I said, silicon is a technology on which pretty much everything is based on today, but silicon has already come to a point where you cannot advance it any further. This is something which all industry roadmaps talk about, all tech leaders talk about, right? So silicon has already come to a point that you cannot advance anything further. Now, this is where the 2D materials come, and as you know, the nature wants advancement, the nature wants things to become better and better. The tech wants advancement, the industry wants advancement. So what can advance? If you look into all options, the 2D material is where everyone is betting, including the industries. I'll show some data later on, right? Now, the other advantage of 2D material, which I'll talk about later, that not only it can replace anything and everything that silicon has done, but can also create newer opportunities, newer applications which so far have not been possible, right? But the fact is that, given the status where the world is today the world is going to work with us, but if we delay any further, we are going to lose this opportunity also to lead or work with others on equal footing, and we will miss this bus as well. Now, this is a little technical slide. The next one, I'll explain the promises of 2D materials. So as I said, the 2D materials can not only replace the what silicon can offer, but it also creates newer opportunities to advance the silicon technology further. For example, suppose today the most advanced chips would integrate close to 10 billion basic building blocks, which are called transistors, right? So now you cannot integrate further. You want to build more advanced functionalities, you want your chips to be more advanced, more capable, you have to integrate more transistors in it, which the silicon cannot cater to. But 2D materials can cater to, because it can be further miniaturized beyond what silicon's limit is. And that is where 2D comes into picture. So 2D materials industry even projects that one can integrate to a trillion transistor kind of a chip. You can imagine the significant, not only the significant performance improvement that you can achieve, but also significant capability building within a single chip that is also possible. Now, on top of that, it also caters to several newer areas which so far was not possible with the conventional technology if we want to call silicon as a conventional technology in the 2D context, right? And a range of areas including quantum technologies. In fact, 2D material is the only platform which basically caters to all 4 verticals of quantum technologies, be it computing, be it communication, be it metrology or sensing, right? Whereas that capability does not exist with any other platform. So now, tomorrow, what you can also do is you can think of building newer applications which are integration of these unique, distinct applications which so far did not happen. I'll talk about this a little later. For example, in this slide, what I call as heterogeneous integration of classical systems and classical quantum systems, right? So for example, you want to build an artificial vision or artificial eye or artificial skin or artificial nose. These ideas are there, in literature since ages, but a practical realization has not happened because of the capability of a single platform which can enable multiple features, which is possible with 2D material or 2D material based silicon platform, which can enable these kind of newer disruptive applications on top of replacing or advancing the previous applications which we talked about, including quantum, for example, right? I mean, so today when you see these quantum computers, you see these big dilution fridges with a small quantum chip sitting. And why there are these big massive systems? Because all the electronics that control the qubit sits outside that dilution fridge. Now you can think of also integrating all that inside the same chip that sits with this quantum computer, right? So there are many disruptive new applications which are possible, which so far we are not there. Now on top of that, you can also augment silicon technology with 2D materials. So that also helps in creating newer disruptive applications which did not happen or were not possible earlier. It also caters to many strategic applications which pretty much every strategic agency looks for, wants for, but they are usually difficult to achieve because of the limitations that silicon or a similar kind of a conventional platform would offer.